welcome back, Organic. I am so excited. Let's continue our organometallics. So this is the second video. If you open this one first, you're going to want to watch the first video that starts up here with our organometallics section. This is our second video. So this first video, we kind of just looked at some vocab, and we looked at why we even care about metals with our organic chemistry. And one of the things I want to do is kind of walk my way through history, but I want to keep in mind some of these reaction, really the importance of why we care about these reactions. I want to keep these in mind when we go through there. And a couple of these first two with normal reagents, that's exactly where I want to start. So if we look at our organometallics, I want to start 120 years ago. Isn't that incredible? We're going to start in 1900. And I just want to point out and have you keep in mind, holy crap, nobody even really knew what an atom looked like yet. The electron was discovered 3 years earlier. We really didn't even have a clear picture of the atom until about the 1930s. And if you look at this chemistry, this was happening at the 1900s. So it was actually a French chemist, Grignard, who discovered mixing magnesium with alkyl halides. So I kind of want to take a minute to draw that out. And this is something that we make alkyl halides in organic chemistry 1, and we use them. We do the same thing in organic chemistry 2. So depending on which semester you're in, we can both learn from this. Organic 2, our unit 2 is all Grignards. We do a lot with our Grignards. So let's take just a generic alkyl halide. And what Grignard discovered in the 1900s, the early 1900s, is if you stir up some elemental magnesium with an alkyl halide, it is very specific to literally insert into this bond. So remember, with organometallics, we're not going to draw this mechanism. This is not a polar or radical mechanism like we've been drawing for organic chemistry. This would be a complex. We'll do an insertion in here. This would be a completely different type of mechanism. So what we typically draw is that magnesium literally inserts itself right here in that bond. Okay, now this is what's given the term a Grignard reagent. Now, I just want to start here because I want to hit some vocab. This is awesome. So this is exactly 2 of the perfect reasons why we want to use some metals with our organic chemistry. The first one is, let's take a look at this starting alkyl halide. Okay, when we make these in OChem 1, the first thing we look at is, let's draw a polar arrow there and look at the reactivity. This carbon now has a partial positive. Your bromine's got a partial negative. So it actually makes a really good electrophile. We see this in OChem 1. This is what we use for our electrophiles in our SN2 chemistry, in our E2 chemistry, our SN1, E1 chemistry. These make good electrophiles. So you've got a partial positive on that carbon. Okay, then now check this out. You add some magnesium, and now which way are you going to draw your polar arrow? If you find magnesium on a periodic table, you're going to notice, if we just draw a little mini periodic table here, magnesium is up over here, carbon is over here. So now which way does our polar arrow go? Your polar arrow now goes opposite. In fact, it's so opposite that now our charges are reversed. We have a partial negative on our carbon, partial positive on our magnesium. But in fact, you draw it like this sometimes in organic texts, and you'll see it in organic literature, but that's not really what that bond looks like. In fact, magnesium and carbon are so different. That is actually an ionic bond. So what you would really see is a negative on your carbon, and you'd have that positive over here with your magnesium. That's a little bit more of an ionic bond and not a covalent bond. So it's kind of traditional to see it drawn like this, but know in your heart that it's actually really pretty much an ionic bond, and you've got a negative on your carbon. So look what our metal just did. It did two things that are so important for organometallic chemistry. The first thing it did was drastically change the actual reactivity on that substrate. You went from a positive carbon to a negative carbon, okay? And look how specific it is. That magnesium will only insert in between a carbon halogen bond. That's it. So you could have all kinds of stuff in your substrate, and that magnesium is going to be so selective, it will insert between that carbon and bromine bond, even if there's other stuff in that compound. So that's why for the last 120 years, our metals have found their way into organic chemistry, and it's been amazing because they do things that are not traditionally possible. Let's do a quick comparison. Let's compare acids and bases. How in the world could you ever make that carbon minus in traditional chemistry? So let's just pause. Let's think about this right here. You just made a negative on that carbon. How would you do that with 1980s air quotes normal chemistry? Well, we would have to set up an alkane. We'd have to treat it with the strongest base we could think of. And if it was 100 years ago, maybe we're thinking sodium hydroxide. If you're a little bit more modern with your organic chemistry, maybe you're thinking something like LDA. We mix a super strong base, the strongest we could even think of. We try to have that equilibrium, that acid-base chemistry. You would have to deprotonate that alkane in order to make that reaction happen. Your strong base is going to have to do that, leave those electrons behind in order to make that negative right there. And then let's say if you use sodium hydroxide, what's your byproduct? Water. Okay. Is this reaction even possible? Okay, let's look at how we evaluate that. How in the world would you evaluate your acid-base chemistry? You're going to compare pKa's. Compare the pKa of any kind of alkane. You are in the range of 50s to 60s in your pKa. And then what do you compare it to on the product side? Your pKa of water. 16. Your equilibrium is going to be skewed so far to the left that you aren't even going to get that reaction to happen. Remember that pKa is a log function. That is not a normal comparison of 50 to 16. That is a logarithmic difference. That reaction isn't possible. There's no way you are going to make this from normal acid-base chemistry. But yet, holy crap, you can make it right here by tossing in some magnesium. And not only can you make that compound, you're going to make it pretty darn selective and only that compound in a pretty clean fashion. So this is why metals have been around for 120 years. They do all kinds of chemistry that's pretty awesome. In OChem 2, even though the Grignard has been around for 120 years, you're going to use this thing on almost every test in OChem 2. It's a phenomenal base and a phenomenal nucleophile. We see it in both. Okay. So let's move on a little bit through history. So we've got some more metals coming out in history. Hydrogenation, actually, we will see in OChem 1 and in OChem 2. This reaction, if you can believe it, has been around since 1912. So after Grignard in 1900 came another French chemist who was developing a reaction. Oh, holy cow, what did I do? Sorry, y'all, I just started over. All right, so developing another reaction, and this one just literally shows us what metals are good for yet again. Let's take something like an alkene, and if you were to just stir this up with hydrogen, in fact, let's draw the bonds to hydrogen. If you were to mix these two, you can stir them forever and likely have nothing happen. You could maybe add a phenomenal amount of heat and pressure, and you might get a small little bit of a reaction, but nothing is really going to happen here. You've got a fairly nonpolar bond here, pretty nonpolar bond there. The only thing you really can do with these is light them on fire. So what he discovered in 1912 was if you put in a metal, specifically palladium, holy cow, you got this amazing reduction reaction where you added those hydrogens to that alkene. Now this we're going to see in OChem 1. This is part of our reductions, and we'll see this in OChem 2 as well. This is how you reduce a double bond. It would not happen if you didn't have that palladium catalyst. What palladium does is it inserts hydrogen. It inserts itself right into that bond. So you end up with a palladium that now has hydrogen inserted on its surface. Palladium is a solid. It stays a solid. And then now palladium can literally deliver those hydrogens to that alkene. And then you end up with your product. So this reaction has been used forever. It's been used in everything from thermochemical studies to it's huge in our oil industry, meaning like vegetable oils and things. This is how you saturate oils. There's all kinds of uses for this. And this is using an organometallic, using palladium. We see that quite often in organic chemistry. And then as we cruise along, those studies with magnesium actually sparked, sorry, that was funny because things are flammable in these reactions. All right, it sparked trying other metals. So what else can you insert into your alkyl halides? So starting in the 1930s, they started, oh, that's really too bold, isn't it? Starting in the 1930s, using other metals started really to become popular. Let's take our alkyl halide again. And the first one, and you know what I love about these reactions is they are still used today all the time. They're amazing. So let's start with our alkyl halide. Turns out magnesium is not the only metal that will insert. Lithium will also insert, often drawn like this, where lithium is inserting in between that carbon-halogen bond, very similar to our Grignard. If you ever wonder why our strongest bases we looked at in OChem 1 and in OChem 2 are our N-butyl lithium versions of N-butyl lithium, why it was lithium, that's this reaction. If we draw our polar arrows, it's very similar to magnesium. You start with something that's got a partial positive on your carbon, and you end up with the exact opposite. In fact, lithium does not make a covalent bond, even though it's conventional to draw it this way. Really, what that is an ionic bond where your electrons are on carbon and your lithium has a plus charge. So you've now made a phenomenal base and nucleophile. Again, very selective, and you've just gone from a really good electrophile to the opposite, to a base or a nucleophile. And this chemistry would not be possible with just a strong base. We looked at that with the pKa difference with magnesium. It just isn't possible. So this lithium-halogen exchange has been around for about 90 years and still used every single day to make those strong carbon bases. And then what came after the lithium-halogen exchange in the 1930s was actually one of my favorite reagents that we are going to use in both OChem 1 and OChem 2. We're going to use the Gilman reagent in two particular instances in both classes. So let's tackle the OChem 1 version. That's our Corey-House reaction. What happens is we take those alkyl lithium compounds, and Gilman actually studied those lithium compounds. And then he did something sassy. He threw another metal in there. So let me give you an example. Why do you even give a crap? If I were to take just two of these lithium compounds, wouldn't it be awesome if you could actually stick them together and like use one of these, or even that wouldn't work, would it? Because you've got a minus here and a minus here. You can't react a minus and a minus. Not going to happen. Now you're breaking all kinds of physics rules. Well, wouldn't it be really awesome? What if we could take these two? And now look at that partnership. What if your lithium compound was a negative and you took your alkyl halide as a nice partial positive? Well, couldn't you react this as a nucleophile, this as an electrophile, and you'd have the world's sassiest SN2? And you could literally start building alkane chains and connect them together. Well, that would be perfect in theory. And that is exactly where Gilman started. He really wanted to be able to take two sides of some sort of alkane chain and combine them into a coupling reaction. It didn't work for squat. It was actually quite terrible. The yields were terrible. It didn't do at all what he was hoping it would do. And then just serendipity, good science, however you want to look at it, what he did, and here's some of this I think is up in this paragraph. So he actually tried to do this reaction directly that we just wrote out there, and it sucked. All right, so serendipity, good science, however you want to view it, he decided to try it again, only throw in a little bit of copper. So let's take that lithium compound, let's treat it with some copper iodide first. And what he did was, this is so funny, but I'm going to draw it weird and then explain it. But what he ended up doing was making this cuprate compound. Now, this is what's given the name Gilman. I'll explain that too in just a second. And then if he reacted this Gilman with that alkyl halide, son of a motherless goat, it worked. And it worked awesome. It literally coupled those two halves. That writing looked terrible. Literally, we just coupled those two compounds. All right, let's explain first this and this. Okay, copper is one of our transition metals. Copper can bond in different ways. Now we're talking our 18 electron role. Copper is unsaturated in here, and it can take on an insert, but it's going to do one of those oxidative additions into your copper. So what happens, there's a little baby mechanism up here. You can find this one on Wikipedia that is kind of helpful. But what happens is when copper inserts here into this bond, it actually takes on two. And we're not going to get that deep into it. It depends on that electron count. If I'm not mistaken, you're going from 14 to 16 to 18 electrons in this transition. You start with your Gilman and you end up taking on two of these onto your copper, and then you still have room to take on one more of these, and then copper spits out and forms a bond between this carbon and this carbon. Okay, that was intense. So I feel like we need to do another one of these. We're literally taking this carbon, and copper then does one of those reductive eliminations and spits it out. And you're left with some copper salts, and you've literally stuck those two carbons together. And that is called a coupling reaction. You are sticking those together in that fashion. Remember, we don't draw the mechanisms for these, but the only reason this happens is that copper has that space to take on those bonds, and then it's extremely selective and it spits out that coupled partner at the end of the reaction. So what's fascinating to me is that Gilman stumbled on this right as even just the normal picture we think of as an atom is emerging. I mean, they didn't even know neutrons existed until the 1930s, and that's when this reaction was discovered. So it has been used a lot, but I'm not sure how well understood it is. It's one of those things that it really works well, but it's hard to trap those intermediates. They are likely a large complex with copper, and you just know at the end you end up with that coupled product. Let me show you a shortcut to the Gilman, because we're going to be using it quite a bit. How the Gilman works. Go ahead and take a screenshot real quick, and I'm gonna erase here, and I'm gonna show another one. What the Gilman is really good for, we have two reactions. The OChem 1 reaction, which is this coupling reaction. So let's draw one of those. Let's give an example of those. And then my OChem 1 students, you will have a whole video on the Gilman. So it's really good for that coupling reaction, that Corey-House reaction, where you can take two alkanes and you can couple them. So you can take any kind of alkyl halide, typically a bromide. Let's put an R group there, meaning any alkane. And then you can treat it first with lithium, second with copper iodide. And now you're going to make a Gilman reagent. That Gilman reagent, take two of these, and then substitute your copper where your bromine was. Now, out of this whole complex mixture, only one reacts, one stays on your copper, and then the carbon you react is right here. So now you can mix it with any other alkyl halide. In fact, let's mix it up a little bit. Let's take this reagent we just made, and let's mix it with a ring. Okay. You can mix that with any other alkyl halide. Isn't that awesome? And now we're going to literally stick this carbon with this carbon. So the carbon attached to your copper, the carbon attached to your bromine, those two will couple. So let's draw the product. Let's take our alkane. I'm going to draw pink where you just coupled. And then let's connect our Gilman reagent. So this part comes from your Gilman reagent. This part comes from your alkyl halide. And you just did a coupling. So remember the organometallics, we talked about how they're phenomenally specific. And so these alkane-alkane coupling reactions are awesome, because you could potentially start with methane and make anything, because you can now couple all of your alkanes together. That's a hint for my OChem 1 class. Isn't that fun? Copper is also very specific for another reaction. My OChem 2 students, check this out. This is our unit 4. If I were to take a ketone, and not any old ketone, something in conjugation, okay, this is a conjugated or in conjugation ketone. Our copper is phenomenally selective. Let's take that same reagent that we just made. It is selective to react right here. This is called a 1,4 addition. And my OChem 2 people, you will have your own video on 1,4 additions. Gilmans are very specific. They add in only that one place, and you end up literally forming your bond here to your Gilman reaction. Isn't that awesome? They are very specific for two reactions. They do an alkane-alkane coupling reaction, that's the Corey-House, and then they are very good at a 1,4 addition. Now, why do you give a crap? Okay, my OChem 2 people, let's compare that same reaction to the Grignard, and let's see the difference. If I were to take this and add our Grignard reagent, it does not go in the same place. In fact, it would go right here. So you are going to have your OH there. You would keep your double bond, and your Gilman, or I'm sorry, your Grignard adds 1,2. So this is considered a 1,4 addition. This is considered a 1,2 addition. So two different metals, two different places they react. Same idea, same polarity in your bonds, but yet they react in two totally different places. Now, if this were just normal chemistry and you just had a negative on a carbon, it would go wherever it's going to go the easiest, but you throw in those two metals and now it's very specific. All right, let me pause this one and then we'll start another video for the rest of it. So I hope that you all can